Very good morning. Today we are going to see a problem on Thevenin's theorem and as well as the Norton's theorem. Take down this problem. Find the Thevenin's equivalent circuit at the terminals A and B in the circuit as shown in the figure below. Hence, draw the Norton's equivalent circuit. So we need to find out the Thevenin's equivalent circuit and as well as the Norton's equivalent circuit. Here, A and B is clearly given here and a circuit is given in this shape. So by seeing this circuit, don't think like it is it is kind of Wheatstone bridge. But the thing is that we need to solve the Thevenin's equivalent circuit and as well as the Norton's equivalent circuit. Now what we are doing is we are open circuiting this terminals A and B. That is the first step in the Thevenin's equivalent circuit. So here by open circuit, what I'm doing is we are redrawing the circuit like this for easy understanding, because this 80 ohms and 20 ohms are in like that. We are just redrawing the circuit like this. Okay, and here also 10 ohms and 90 ohms we are redrawing like this, and same A and B we are marking. Now we are short circuiting the voltage source. So here you need to short circuit the voltage source. So if you see this circuit, this 10 ohms and 90 ohms are in parallel, and 80 ohms and 20 ohms are in parallel. So if you find out the equivalent circuit for this 10 ohms and 90 ohms, it is 10 into 90 divided by 90 plus 10. So while simplifying, we'll get as 9 ohms. Here also 80 and 20 ohms are in parallel. So if you find the equivalent circuit, it is 80 into 20 divided by 80 plus 20. It is 16 ohms. So now these two are in series with this. Okay, this 9 ohms and 16 ohms are in series. This 9 ohms and this circuit you can draw like this, because this two simplifying we got 16 ohms. This two, if you simplify, we got 9 ohms. So 16 ohms and 9 ohms are in series. So then if you find out the R Thevenin resistance, then it is 16 ohms plus 9 ohms. That is nothing but 25 ohms. That is the RTH. Now we need to find out the VTH or VOC, that is open circuit across this point A, and open circuit voltage or Thevenin's equivalent voltage across this point A and B. The same circuit we need to draw once again. Now here, if you see here, voltage source is there. Which method is very easy thing. There are many methods to solve. Which method is very easy in the sense by using the loop analysis or mesh analysis. So by applying the, so here I am drawing one this current direction here like this I1, here like this I2. So from loop 1 we are applying the loop or mesh analysis. So it is flow. This current is flowing from minus to plus. So minus to plus we are taking this minus 40 plus 80 I1 plus 20 I1 is equal to 0. Well, simplifying, we'll get 100 I1 is equal to 40. Further simplifying, we got it as I1 is equal to 0.4 amperes. Next, in loop 2, this loop 2, we are just applying here. So 10 into I2 plus 40, because it is flowing from plus to minus, so it is plus 40. Next, plus 90, I2 is equal to 0. Further simplifying, we got I2 as minus 0.4 amperes. So we need this particular VTH we need. VTH we need. So we got I1 and I2 here. So voltage in 20 ohm resistances. So this we are finding out voltage in 20 ohm resistor and voltage in 90 ohm resistor. So together that plus is nothing but this VTH or VOC. Here the voltage in the 20 ohm resistance is nothing but V1 is equal to I1 into 20. So I1 we got it as 0.4 into 20. So further simplifying, we got V1 as 8 volts. Similarly, the voltage in 90 ohm resistance is V2 is equal to I2 into 90. I2 we got it from the previous calculation as a minus 0.4 amperes. So just as we are substituting here into 90, we got V2 as minus 36 volts. Now we need to find out the voltage across this point A and B. That is nothing but VAB. That is V1 plus V2. So here this plus this 8 plus uh, minus 36. So 8 plus minus 36 is minus 28 volts. That is a VOC or Thevenin or VAB is nothing but minus 28 volts. Now we are drawing the Thevenin's equivalent circuit, that is a minus 28 volts, that series with the RTH. RTH we calculated as 25 ohms here. RTH already we calculated as 25 ohms here. That we are simply we are substituting here RTH, and that open circuit, that A and B na, that resistance also we are adding over here. In question they asked only Thevenin's equivalent circuit, so we have drawn the Thevenin's equivalent circuit. Suppose if they ask the current to that particular load resistance, then the load resistance value will be given, but in question itself they have given us just R. So just we need to draw the Thevenin's equivalent circuit. That's all. Again, they asked to formulate the Norton's. So two questions are given. First one is Thevenin's equivalent circuit. The second one is Norton's equivalent circuit. So Norton's equivalent circuit also we need to draw. So next part is to draw the Norton's equivalent circuit. Thevenin's we drawn. Norton's theorem and its equivalent circuit we need to draw. So RTH and RN is nothing but RTH we already got it. That is nothing but RN, that is equal to 25 ohms. Now we need to find out a Norton's current. Okay, so we need to short circuit this particular load resistance. We are already we open, no, that we need to short circuit. Here we need to find out the Norton's current. This is in this point we need to find out the Norton's current. That is nothing but I3. Now the same circuit I have redrawn once again. Now three loops are there. If you we need to short circuit the particular that load points A and B, and we need to find out IN over here. That is nothing but Norton's theorem. That procedure also I will give in the description. You just once you go through it. Now three loops are there. Here in the first loop we are finding out the that is yeah, first loop we are taking this I1. Second loop we are taking this I2, and third loop we are taking this I3. From loop 1, the current is flowing like this, that is minus to plus. So minus to plus is minus 40. In that term, we are taking this plus 80 into I1 plus 20 into I1 minus I3 is equal to 0. Further simplifying, we got it as a 100 I1 minus 20 I3 is equal to 40. So I2 is not this, just you add as 0 I2. For simplifying, it will be very easy. So 100 I1 plus 0 I2 minus 20 I3 is equal to 40. Take this as equation number 1. Next, in loop 2, what is in loop 2? We need to find out 10 I2 plus 4. So it is flowing like this. So plus 40 plus 90 into I2 minus I3 is equal to 0. That also we need to find out. So here further simplifying, we got it as a my 0 I1 plus 100 I2 plus 100 I2. Next is minus 90 I3 is equal to minus 40. Take this as equation number 2. Similarly, in the loop 3, same thing we need to do. Loop 3, what? First 90 is there. So 90 I3 minus I2, okay, plus 20 into I3 minus I1 is equal to 0. 90 into I3 minus I2 plus 20 into I3 minus I1 is equal to 0. Further simplifying, we got the value as minus 20 I1 minus 90 I2 plus 110 I3 is equal to 0. Take this as equation number 3. Solving this 3 equation by using your scientific calculator is very simple. Unknowns are 3. So just you need to calculate. Then further calculating, we got the answer as I1 is equal to minus 0.176 amperes, I2 is equal to 1.408 amperes, I3 is equal to 1.12 amperes. So now we need to find out IN. IN is nothing but in this particular circuit, IN is nothing but I3. So because IN, we need to calculate a short circuit current. So that is, this current is flowing in this particular part. So this I3 is nothing but IN. So I3, what we calculated is that is the IN. So I3 is equal to IN, that is equal to 1.12. So IN is 1.12. Now we need to draw the Norton's equivalent circuit. Norton's equivalent circuit, how to draw? We need to draw in parallel. Okay, parallel, that is IN is equal to 1.12 amperes. Next, that RN we calculated no from the previous in Thevenin circuit. RN is equal to RT. That we calculated as RN as 25 ohms. Next, load resistance, that A and B point, that also should be in the parallel. That resistance is given as R. Just like that, we are adding over here. So this is the Norton's equivalent circuit for this particular circuit given in the problem, and as well as we drawn the Thevenin's equivalent circuit. Just they need to draw the Thevenin's equivalent circuit and Norton equivalent circuit. So in this Thevenin's equivalent circuit, the voltage is we got this minus 28 volts. So you can reverse this terminal. That is here. Here you can reverse this terminal and you can draw this Thevenin equivalent circuit, or you can write as minus 28 also, or if you reverse this terminal and if you write 28 volt, that is also okay for this particular circuit shown in the given in the figure, given in the circuit, given in the figure, that is given in the circuit. Thank you.